All right. Let us look at one more very interesting example. Okay, this is example number 7, and let us look at the following equation, which we have studied many times, which is called the moving average filter. Moving average filter. Okay, moving average filter is y of n is equal to 1 over n. I am averaging over n samples. The last n samples are average, k equal to 0 through n minus 1, x of n minus k. Okay, this is a filter that we know how to implement. Now, if I were to ask you to implement this equation as a linear constant coefficient difference equation. Remember, how to represent difference equations. This will be the structure that you will obtain for me. Okay, so there is a summation. You have a string of delays. So, this is delay number 1, this is delay number n minus 1. I need a total of n minus 1 delays. Each of these delayed signals gets added onto the summation element. Okay, and the last one comes to the summation also. Okay, and the output we scale by a factor of 1 over n, and this is my output y of n, this is my input x of n, this will be x of n minus 1, this will be x of n minus 2, this will be x of n minus 1. Okay. So, this is the implementation of the structure. Again, I am sure that you are familiar with this and comfortable with this. Now, I will ask you to apply the discrete time Fourier transform. Apply discrete time Fourier transform. Okay. On the left hand side, we get y e power j omega, and on the right hand side, we get 1 over n x e of j omega, that is the first term. The second term is the discrete time Fourier transform of x of n minus 1. So, you get e power minus j omega x e of j omega, and similarly all the way to the last term, which gives you e power minus j omega n minus 1 into x e of j omega. You can see that x e of j omega is common. So, we get x e of j omega at the output, scale factor of 1 over n, and what is inside is 1 e power minus j omega, a finite duration geometric series, j omega n minus 1. Okay. So, I am sure you are comfortable so far. Moving average filter, I wrote down the expression and then took the discrete time Fourier transform. So, now simplify this expression, you get x e power j omega divided by n, and on this side you get 1 minus e power minus j omega n, geometric series, 1 minus e power minus j omega. Okay. And this is a very interesting result, because we can now rewrite the difference equation, LCCDE. So, I am going to write down the LCCDE in the following manner. So, this is y e of j omega. Okay, cross multiplying, we get y e of j omega 1 minus e power j omega. This is equal to 1 over n x e of j omega 1 minus e power minus j omega n. Okay. So, this is still not in the time domain. So, take the inverse DTFT. Okay. What do you get? You get the LCCDE. The LCCDE says y of n minus y of n minus 1 equal to 1 over n x of n minus, what is this? It is e power minus j omega n times x of omega, x of e of j omega, uppercase n. So, I would get x of n delayed by n units of time. Okay. So, this is a very interesting representation, which then says, I have an alternate way of implementing this result, because I can now draw a structure that looks different, but is able to calculate, make the same calculation as before. So, here is a representation of that signal. Okay. So, I can now draw a structure where I have input x of n. Okay. There is a summation. I am going to pass through a block which will delay by n units of time. So, basically there is only one block. What comes out of this is x of n minus n. Okay. And I am going to take it to the summation, but notice that it is not a addition, but it is going to be a subtraction. So, I put a minus sign there. Okay. Then what do I have on the output side? I have y of n passing through a delay. This will produce y of n minus 1. This will get added to the signal with a plus sign. Okay, remember y of n, if y of n minus 1, if I take it to the other side, it will become plus y of n. So, whatever was the operation on the input signal added to y of n minus 1 is going to be equal to y of n. The only thing that we have to still take care of is a scale factor, do not forget that. So, there is a scale factor which comes in this path. So, x of n minus x of n minus n, scale factor of 1 over n, to that you add y of n minus 1, this is y of n minus 1, that is equal to y. These two structures are identical. They compute exactly the same behavior. And of course, if n was a very large number of delays, you are averaging over a long duration, the number of computations that you will encounter in the first structure is much more than number of computations in this one, because in the second one, for each output you have to compute 2 additions and 1 multiplication, and that is all that is there. And therefore, this is a more optimal structure in terms of number of operations. So, they call it as a canonical structure, canonical form. This you can think of this as a optimal form. Canonical in what sense? In terms of the number of computations. So, two things that we learn from this particular example. One is whenever you have a LTI system, you can take its Fourier transform. It will give you very good insights like what it did for us in terms of filtering. It can also give you very efficient implementation of your time domain operation, because once you convert it into LCCDE, then you can take the Fourier transform, and the Fourier transform enables us to make some simplifications, and therefore this is a very powerful result. Now, one of the things that I would like you to be able to do is to use the discrete time Fourier transform to compute the inverse Fourier transform. Okay, so let us see how we can do that. So this is example, I'm going to call it 7b because it is related to 7a. You can sort of look back and check what it is like. Okay, we are given an LTI system which is represented by the LCCDE, linear constant coefficient difference equation, and the equation is y of n minus y of n minus half y of n minus 1 equal to x of n minus 1/4 x of n minus 1. Okay, I am going to give you a task is to sketch the circuit for implementing this. So, circuit for the LCCDE. Okay, it will look just like this one. Of course, you have to adjust the delays correctly, apply scale factors, but I am sure that you will be able to do that. Okay, that's an important one, and that's. But what I would like to do is apply the discrete time Fourier transform. Apply the discrete time Fourier transform. Now, why are we doing that? Remember that the input-output relationship in any LTI system is y of n is equal to h of n convolved with x of n. Okay. Apply the DTFT. What do you get? Y e of j omega, discrete time Fourier transform, is equal to h e of j omega, the Fourier DTFT of the impulse response times x e of j omega. From this we get the relationship h e of j omega is equal to y e of j omega divided by x e of j omega. Okay. So, ratio of y by x in the DTFT domain is going to give you the discrete time Fourier transform of the impulse response of the LTI system. So, that is what we are trying to work towards. So, y e of j omega minus 1/2 y, this is a delayed version. So, e power minus j omega y e of j omega equal to x e of j omega minus 1/4 e power minus j omega x e of j omega. Okay, group the terms, you get y e of j omega into 1 minus 1/2 of e power minus j omega. Okay, equal to x e of j omega 1 minus 1/4 e power minus j omega. Okay, this then says take the ratio h e of j omega is equal to y e of j omega divided by x e of j omega. Okay, that will basically give us the expression 1 minus 1/4 e power minus j omega divided by 1 minus 1/2 e power minus j omega. You can cross multiply and verify that this is the expression that we get. Now, one last step which is extremely important. Now, two terms are there in the numerator. I would like to split those two terms. So, I am writing it in the following form: 1 divided by 1 minus 1/2 e power minus j omega minus 1/4 a scale factor e power minus j omega divided by 1 minus 1/2 e power minus j omega. Okay. So, this is expression for h e of j omega. Now, what is h of n? H of n will be the inverse discrete time Fourier transform of the first term. Now, remember we had a relationship, if you have a power n u power n, where is our Fourier transform theorems? Maybe it comes in the a power n u of n, 1 over 1 minus a e power minus j omega. That is the result that we have already obtained. So, this term is 1/2 raised to the power n u of n, the corresponding inverse discrete time. This is the sequence that will give you that response. Okay. Now, this is also going to be the same sequence, except that it is delayed by 1 unit of time. Okay. So, you keep the scale factor as is, you get 1/2 delayed by 1 unit of time. 1/2 n becomes n minus 1, u becomes u of n minus 1. Okay. So, this is the impulse response that is characterized by this LCCDE, and this is a very, very useful result and a very useful way of computing the inverse Fourier transform. You look at the Fourier transform pairs that you already know and then use that to obtain the mapping back to the time domain. So, there are two things that we learnt from this. Any LTI system is represented by an LCCDE. We can take the discrete time Fourier transform, take the ratio of y e power j omega divided by x e power j omega, that is a discrete time Fourier transform of the impulse response. If I take the inverse Fourier transform of that, I will get h of n, the impulse response of the LTI system. So, this is a way by which we can solve LCCDEs to get the impulse response, and this is a very efficient way of doing the computation of the inverse Fourier transform.